All right, area under the curve. Area under the curve y equal to f of x, like this function shown here, and the x-axis, here we have the x-axis, area between this curve and the x-axis bounded by x equal to a, this vertical line x equal to a, and this vertical line x equal to b. That is, area under the curve between x equal to a and x equal to b is the definite integral from a through b of the function. So if we want the area under the curve bounded by x equal to a and x equal to b, enclosed by that function and the x-axis, it is the value of the definite integral from a through b. Remember one thing, from the Riemann integration, what we know is we try to divide the entire area, entire interval, onto small sub-intervals of very small width like delta x, like the one shown here. Then we can continue this process. We can divide entire interval into many sub-intervals, and then we construct the rectangles. We add the area of all the rectangles when n goes to infinity, and that is the value of the definite integral. So we already know that concept. So instead of using the limit of the Riemann sum, we are directly going to evaluate this integral using the fundamental theorem of calculus. Remember one thing, when we draw this vertical rectangle, you can see that if I try to move this rectangle, say for example, this rectangle is movable. If I try to move this rectangle to the entire left and up to the entire right, you can see that this rectangle is always between this function and the x-axis. If that is always between the function and the x-axis, then you can evaluate this area using the single integral. Otherwise, you may have more than one integral to evaluate that area. So this is the fundamental concept of area under the curve. We are going to take examples and explore this. Example, determine the area of the shaded region R. Here is that shaded region R in the following figure. So here we have the function y equal to square root of x, and from x equal to 0 up to x equal to 1, the region bounded by the function and the x-axis between x equal to 0 and x equal to 1 is R. We need to find that area. If I try to draw a small rectangle, a small vertical rectangle like this, small vertical rectangle of with delta x, and if you try to move this rectangle all the way to the left of the region and all the way to the right of the region, you'll see that this rectangle will be always between the function and the x-axis. That means this is a single region, and we can evaluate this area, or we can find this area using a single integral. And that will be the integration of this function, integration of square root of x. Let me write that here. Area is equal to integration of square root of x from x equal to 0 up to x equal to 1. X equal to 0 up to x equal to 1 with respect to x. You know that square root of x is x raised to half. So we can evaluate this integral using the power rule. So we increase the power by 1. X raised to, so it already has a power of half. So half plus 1 is 3 over 2. And we divide that by the new power, 3 over 2, evaluated between 0 and 1. Now, we can simplify this using the fundamental theorem of calculus. That is, we plug in upper limit 1, subtract and plug in lower limit 0. So if I plug in 1, it will be 1 raised to 3 over 2, which is 1. 1 over 3 over 2 is 2 over 3, because 1 over is the reciprocal. Then minus and plug in lower limit. If you plug in 0, 0 raised to 3 over 2 is 0. 0 divided by 3 over 2 is 0. So that is equal to 2 over 3, or 0.67. So the area of the region R shown here in this picture is 0.67. Example, determine the area of the shaded region R in the following figure. So here we have the graph of the function y equal to f of x. We have the region R bounded by the function and the x-axis between x equal to 0 here and x equal to 1. If I try to draw a vertical rectangle of width delta x, it will look like this. That is the vertical rectangle of width delta x. And if I move this all the way to the left or all the way to the right, you can see that the rectangle will be always between this function and the x-axis. That means this is a singular region and we can find the area using a single integral. So the area of the region is equal to the definite integral from 0 up to 1 of this function, which is x squared with respect to x. Now, in order to evaluate this integral, we use the power rule. That is, we increase the power by 1 and divide by the new power. So we have x squared. If we increase by 1, it will be x cubed. And we divide by the new power, so x cubed over 3. And we have to evaluate this between 0 and 1. That is by using the fundamental theorem of calculus. If I plug in the upper limit, it will be 1 cubed over 3, which is 1/3. Minus, if I plug in lower limit, it will be 0 cubed over 3, which is 0. So 1/3 minus 0 is 1/3 or 0.33. So that is the area of the region R shown here in this shaded region. Example, determine the area of the shaded region R in the following figure. Here we have the graph of the function y equal to x squared plus 5. And we want to find the area under this curve bounded by x-axis. Then here x equal to 0 and x equal to 3. If I try to draw a vertical rectangle like this, you can see that this rectangle is always between the function and the x-axis when we move to the left or to the right. That means this is a single region and we can find the area. It's a single region and we can find the area using a single integral. So meaning of that is area is equal to the value of definite integral from 0 up to 3. And here we have x squared plus 5 as a function. We are integrating that with respect to x. Now, in order to integrate this, because this is an algebraic function, we can easily use the power rule for the first one. We increase the power by 1 and divide by that new power. So it will be x cubed over 3. And then integration of constant is constant multiplied by x. So it will be 5x because the derivative of 5x is 5. So integration of 5 will be 5x. And this needs to be evaluated between 0 and 3. Must be evaluated between 0 and 3. Which is equal to, now we can evaluate this using the fundamental theorem of calculus. That is, we can plug in the upper limit, subtract and plug in lower limit. So if I plug in upper limit, it will be 3 cubed over 3, which is 27 over 3 or 9, plus 5 times 3, 15, then minus. If I plug in lower limit, it will be 0 cubed, which is 0 over 3 is 0, plus 5 times 0, that is also 0, which is equal to 9 plus 15 is 24. So area of the shaded region R is 24. Example, determine the area of the shaded region R in the following figure. So when we look at this figure carefully, you can see that the region R is bounded by the function y equal to 8 on the top, and below it is bounded by y equal to x cubed. So far, we only know how to find the area of the region bounded by the function above and the x-axis below. So this one is a little different. We can see that there is a function above, and then below it is bounded by the other function y equal to x cubed. So what I'm going to do is, instead of drawing the vertical rectangle, I'm going to try by drawing a horizontal rectangle. If I try to draw a horizontal rectangle like this, suppose if I try to draw a horizontal rectangle like this, now this is along the y-axis, you can see. So the width of the rectangle will be delta y. Instead of drawing a vertical rectangle, I'm drawing horizontal, so that the base of the rectangle is on the y-axis. And if I try to move this rectangle, now if I look at it carefully, if I try to move this rectangle up, down, like this, if I try to move it like this, instead of horizontal, because it has a base on the y-axis, so I'm going to move or slide along the y-axis. If I try to slide along the y-axis, then what I can see is this rectangle is always between this function and the y-axis. Like we used to have the rectangle between the function and the x-axis. Here we have this function, we have this rectangle between the function and the y-axis from y equal to 0. The y value over here is 0. Y equal to 0 up to y equal to 8. So I can find this area by integrating with respect to y. So what I mean by that is this area, let me write that down. So it is the definite integral from 0 up to 8, 0 up to 8. Because I'm sliding this along the y-axis, I have to integrate with respect to y. So this will be integration with respect to y. So dy of a function. So because I'm integrating with respect to y, I have to write this function in terms of y. So I cannot write x cubed here because I'm integrating with respect to y. So I have to find this function in terms of y. So here the function is y equal to x cubed. That is in terms of x. If I want to write this in terms of y, then I have to solve for x. So from here, x will be equal to, here we have x cubed. So if I take 1/3 power on both sides, I'll get the value of x. So x will be equal to y raised to 1/3. So my function is y raised to 1/3. So we set up the integral. Area is equal to the definite integral from 0 through 8 of y raised to 1/3 integrated with respect to y. So this will be equal to, we can simplify this or we can evaluate this using the power rule. So we increase the power by 1. We already have y raised to 1/3. 1/3 plus 1 is 4/3. Y raised to 4/3. Divide that by the new power 4/3. And then evaluate between 0 through 8. Now we can simplify this using the fundamental theorem of calculus. That is, we plug in the upper limit, subtract and plug in the lower limit. We are dividing by 4/3, which is same as multiplying by 3/4. 3/4. And then we are plugging in 8. So it will be 8 raised to 4/3. 8 raised to 4/3. Then minus, we plug in, now we have the 3/4 there because we are dividing by 4/3, which is same as multiplying by 3/4. We plug in the lower limit 0. So 0 raised to 4/3. The second term will be 0 because 0 raised to 4/3 is 0. 0 times 3/4, that will be 0. So we just need to simplify the first one, which is 3/4 multiplied to, look at the screen carefully, 8 raised to 4/3. Power 1/3 is a cube root. Cube root of 8 is 2. And then we are raising 2 to the 4. 2 raised to 4 is 16. 3/4 of 16 is 12. So the area of this shaded region here is 12. Now I'm going to solve this problem by integrating with respect to x. If I look at the region here, we have already seen that this is the region bounded by the function y equal to 8 and the second function that is y equal to x cubed. So if I try to draw a vertical rectangle, like this one, say for example, that is my vertical rectangle of width delta x, then you can see that this rectangle will always be between, whether you move it all the way to the left or all the way to the right, this is always between this function y equal to 8 and this function here, which is y equal to x cubed. Between this one is x equal to 0. So the left end of the area is x equal to 0. And the right end over here, we don't know what is that point, but we can easily find that point. If I can find that point, then I know the right end also. So the y value over there is 8. You can clearly see the y value is 8 and x cubed is equal to 8. That means x equal to 2. So this must be x equal to 2 because 2 cubed will be 8. So that this point will be 2, 8. This point is 2, 8. Now, once we know the lower boundary for the area, which is x equal to 0, and also the upper boundary for the area x equal to 2, and we know that the area is between two functions. The first function is y equal to 8, and the second function is y equal to x cubed. Now, we can easily find this area by integrating with respect to x. And this is how we can set up the integral. Area A is the definite integral from 0 up to 2. Since this area is bounded by two functions, the way we write the area or definite integral is the upper function for this reason. For this reason, the upper function is y equal to 8 minus the lower function. The lower function bounding the area is this function, which is y equal to x cubed. So we have to integrate this with respect to x to get the value of this definite, to get the value of this area, which is shown here in shaded region. Now let's evaluate this integral. Integration of 8 with respect to x is 8x. Then minus integration of x cubed is x to the 4 over 4. And we have to evaluate this between 0 and 2, which is equal to, we can evaluate using the fundamental theorem of calculus. We plug in the upper limit. So 8 times 2, 16, minus, we plug in 2. So 2 raised to 4 is 16. 16 over 4 is 4. Minus, and plug in lower limit. If you plug in 0, 8 times 0 is 0. Minus 0 raised to 4 over 4 is also 0. So the second term is completely 0. The first one is 16 minus 4, which is 12. So we get the same result by integrating with respect to x. So you can integrate with respect to x or with respect to y, and you will get the same result.